So first announcement is, it turns out there are a couple of holidays when we're supposed to be teaching. And it's the first two, January 15th, Feb 19th. There'll be no class then, so I'm going to suggest makeup classes on 2 Fridays, Jan 26th and Feb 9. Again, that's 3 Fridays I'm mentioning out of 20 classes. I hope your schedule allows that. But do mark that down. So next Monday, no class. It's Martin Luther King Day. Celebrate. And then President's Day gets us as well. So teaching Mondays and Wednesdays is a bad idea. Just messes things up, but here we are. Okay. So I want to summarize some of the things we did Monday, just to bring you back up to speed. Introduce the Z transform. It's defined on a function in time, which is discrete in time and discrete in value. And it has a Z transform denoted that way, with the definition of the Z transform we went through. It's simply tagging each of the fn's with a quantity z to the n, summing, and getting a single function, so you can unwind it later if you see the coefficients of z to the n. Here is perhaps the most important pair. For this time function, you get this z transform. Also, I made the comment in passing that if you have two such sequences convolved, the transform of the convolution is the product of the transforms of each. So we talked about how to go into the transform domain. We talked about how to get out of it. So if you want to go from f of z back to f of n, namely that way, the procedure is to use something called a partial fraction expansion. Partial fraction expansion, to remind you, says if the function you have is a rational function, namely the ratio of two polynomials, and the degree of the numerator is strictly less than the degree of the denominator, then follow the following procedure. And if this is not true, just divide the numerator by the denominator, pick up powers of z till you get something which satisfies that degree condition, and then proceed. Next step is to factor d of z. That's the hard part. It's the only hard part. So to factor a polynomial, once you have that, the denominator will look like this. And the one I've written here shows a bunch of unique roots of multiplicity 1. Now, if the multiplicity is higher than 1, say 2, then you have to get a little more sophisticated in inverting it. I don't want to take you through that torture now, it's in the book. In this case, f of z with this denominator then can be written as this sum of unique roots. And given this pair that you've memorized in your sleep, each one of these separately inverts back to time domain, and you're done. Okay, by the way, when you look at this, if I set z equal to 1, what do I get for f of z? F of 1. What is f of 1 then? Come on, z equals 1, that's 1. So it's a summation of the entire sequence. So you get that for free once you have f of z. And we're going to make use of that because the sum of all the terms we're going to deal with will be probabilities, and the sum of the probabilities is 1. So you know already f of 1 should be 1 if it's a probability distribution we've converted. We'll get to that later, just a comment on the side. Okay, now, we then talked about Laplace transforms. And again, the same thing. You've got a function of time for positive time. By the way, this is also, I guess, yes, I did write it down here. This is only for positive time indices. Same here. That's the ones we're after. It's denoted, its transform is denoted that way. The definition is simply not tagging it with z to the n, but with e to the minus st, where s is a complex number, just as z was a complex number. The most important pair, similar to the one above, is its exponential instead of the geometric. Again, convolution in time gives you product in transform domain. And to invert f of s back to f of t, use partial fraction expansions again. Same procedure. Slightly different terms here. You get an S instead of a Z, and you go ahead, and it's in the book. So we also use the Z transform as a way to solve difference equations. So going back to the Z transform, difference equations, you got Fn as a function of Fn minus 1, Fn minus 2, etc. You want to find the sequence Fn explicitly. So what are you doing? This is a rather important process I'm describing here. We're going to use it over and over again. Right now, you only see it being used in examples. You'll see it being used when we get to probability problems and queuing problems. First, you take the original equation and you multiply the nth equation, f sub n, by z to the n, and sum over the range for which the equation you were given holds. N equals 1, n equals 2 to infinity, or whatever. The example we used had n equals 2 to infinity. So you'd sum from 2 to infinity. Once you do that, you want to look at each of the terms in this equation. There is, each of those terms has an Fn times z to the n summed. But there may be an Fn minus 1 times z to the n summed. So I want you to match the power of z with the subscript n on the function, which means take out powers of z, add powers of z, multiply by z to the k over z to the k. So you can match the exponent on the z to be that of the subscript for f. And then you'll notice f of z all over the place. And in some cases, you'll have what looks like f of z, but you're missing a few terms. So if you write f of z, you got to give back those terms. So you'll have f of z minus the missing terms you added inadvertently. Once you got that, it's a simple algebraic problem to solve f of z. You apply the initial conditions for which this difference equation gave you, and then you invert. And how do you invert? Partial fraction expansion. Done. And we did an example. So now I want to go to, instead of difference equations, I want to go to differential equations. So let's look at that now at the start of this lecture. And this is a very short description because it's very much like that for difference equations. And I'm going to use an example as I did with the difference equations. And the example is this one. It says the second derivative of f of t with respect to t minus 6 times the first derivative plus 9 times the function itself is equal to something. In this case, we're going to make it 2t. And of course, I've cooked up this equation, so it's relatively straightforward. And I need some additional information. I think it was you who told me what it is last time. Initial conditions. When I want initial conditions, I'm going to point to you. Okay? So I'm going to give you, how many initial conditions do I need to solve a second-order differential equation? 2. That's right. 2. So let's make them up. So I'm going to give you 2 initial conditions. And I'm going to choose easy ones, so the example is rather easy. I'm going to say that f of 0 minus, and I'll explain the minus in a moment, is equal to 0. And the first derivative at 0 minus is also equal to 0. Okay. Now, in order to go ahead, I'm going to use Laplace transforms. Why? So I don't have to guess for a particular solution. I don't have to guess. If I stayed in the time domain, I'd look for the homogeneous solution, maybe remember that, and the particular solution which you have to guess, and God knows if you guess correct. No guessing here. That's another advantage of this procedure. Okay? So I'm going to use transforms. So let's take this equation and let's take the equation, and what is that going to give me if I transform it? Well, you have to look in the properties of a Laplace transform to understand what does a differential of a function do in terms of its transform. And it turns out if you differentiate twice, you get s squared times the function. Okay? In fact, the general solution is this. I'll write down This is one of the entries in one of your tables, and I'm going to need a little more room to write this down. It says if I have the f nth derivative with respect to t, that is going to give me in transform domain s to the n times f star of s. F star of s is the transform of f of t, minus s to the n minus 1 times f of 0 minus s to the n minus 2 power of the first derivative of f at 0 minus plus dot 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 all the way out to minus s to the 0th power, which happens to be 1, f n minus first derivative at 0. That is pair number, that's the footnote in table I3. So let's go look at it just to remind you. Table I3. This little footnote is essentially what I just wrote down. It's its first line here. It works in both directions. This is for the differential. This is for the integral. And I just basically wrote this down for you. So it's in your book. You don't have to worry about copying my ugly writing from the screen. And similarly, we're going to take advantage of pair 10 in table 4, which is this one at the bottom of the page, which talks about how I deal with multiple roots. And it's this combination that we'll be taking advantage of. So I'm going to write it down rather easily. So going back to taking advantage of what I just wrote down and showed you, we'll basically get s squared. We have a second derivative up here, you see. Second, so I'm going to get an s squared. Oops. Times f star of s. But remember, I have to take away 2 terms as well. I'm going to take away s times f of 0 minus the first derivative of f at 0 minus. And then the next term in the equation was 6 times the first derivative, minus 6. So I'm going to get minus 6. And the first derivative is going to give me s f star of s again. And I only need to take away 1 term, which is minus, basically, f prime. So I'm going to get a plus sign, 6 f of 0 minus. And that, then I get plus, going back to the equation, it's 9 times the function itself. So it's 9 times f star of s. And all of that for this term on the right, which is 2t, at the item number 10 I showed you a moment ago, gives you a 2 over s squared. T turns out to 1 over s squared in time domain, in frequency domain. Okay. Now, happily, we have some initial conditions. F0, f prime of 0 is 0, and f of 0 is 0. So all these terms go away, and I'm left with, and by the way, this process I just quickly wrote down is equivalent to what we said in the expression for solving equations, namely, take the thing fn and match z to the n with it, fn minus 1, z to the n minus 1. That's what this is doing, but all in one step. I'm matching basically the s powers with the size of how many differentials I get. So no differentials, I get 1 times this. 1 differential, I get an s. 2 differentials, I get s squared, etc. That was matching the terms. Okay, so let's undo all that. And now f of s appears all over here, solve for it. So I'm going to get, if we do the little bit of tiny algebra, I get the following. I get 2 over s squared, that's this term on the right, over s squared minus 6s plus 9. And if I multiply by s squared upstairs and downstairs, I'll get 2 over s squared times s minus 3 squared. Whoops. In other words, the roots of this denominator, it's a double root at s equals 3. And now using my partial fraction expansion, if you recall, here I got a double root, so I'm going to get b11 over s squared plus b12 over s. Notice the s squared right here, I'm trying to get you familiar with this manipulation. This s squared is a double root at s equals 0. So that's why I get 2 terms over here. This is like the multiple root case, but the root happens to be 0. Okay. So going on, plus I'm going to get a b21, the second root coefficient, over s minus 3 squared, plus a b22 over s minus 3. And if you figure out what the b11 and the bij's are, simple calculation, what's the basic approach? If you want, say, b21, you multiply the function you have. Let me go back to a little right here. You multiply this whole function. Well, it's easier to look at this one. Multiply by s minus 3 squared, then set s equal to 3 in what remains, and you get the b21, etc. So working that out, I'll get 2 over 9. Let me write it this way. That's b11 over s squared plus 4/27 over s itself plus 2/9 s minus 3 squared plus minus 4/27 over s minus 3. So f of t, which is the inverse of all of that, you immediately recognize the things or go to the table and get it. 2 over 9 will multiply t. As I said, t turns into 1 over s squared. Plus I get 4/27, 1 over s becomes 1. Plus 2/9. The s minus 3 squared gives me t e to the minus 3t from the tables. And then I get minus 4/27. And what does a constant over s minus 3 give me? What does that invert to? That's the one you should remember. Anybody? You're looking at it here if you peek. It's just e to the minus 3t. Okay. Done. That's the answer. So this was a rather short description of how you deal with Laplace transforms to solve linear difference equations, linear differential equations. Okay. Now these are tools I'm developing for you, which we're going to use later. So this is an investment you're making. You may not have seen why you're learning this. You have to trust me, or maybe you see the beauty of it. How many of you see the beauty of it? Ah, is that a question or yes? That's a question. No beauty. Okay. What's your question?
Shouldn't that be plus 3t on the exponent if it's s minus 3 in the denominator? Should be e to the 3t, right? Not e to the minus 3.
Let's see. Let's check the table. Let's see if you're correct. You may be. That was. You're right. Plus a goes to minus, minus a goes to plus. Thank you. Correct you are. So let's fix that. So I get back to the beauty question, however. Obviously, you see the beauty of it. Thank you. He does. Yes.
Should that be 427 times the delta of t, like the delta function?
For which one? No.
The second one.
The constant. If this looked like, let me get my funny over here. If it was simply this without the s, then it's an impulse. It's a delta function. Okay, the Kronecker delta. But with the s, you get a t. Proof, go to the tables if you believe the tables. But good question. Anybody else have any good questions or comments? Now do you see the beauty? All right, you'll see it when we go on. Okay, so let's now go to the probability material. Let me pull that up. Okay, let me clean this up so. Okay. So new topic, I'll use a new page. This is going to be Appendix 2, Probability Theory Refresher. And I call it a refresher because hopefully you've seen some of this before. If you haven't, then what I'm going through is not so much proof of the things I'm going to say, but a description and some indication as to why they're true. So this is Appendix 2 now. So what we're trying to do, a probability system is a mathematical representation of a physical experiment. So when you do an experiment, and I'm going to choose a particular experiment here, one that you may or may not enjoy. Come on. Oh, by the way, I went to the lecture this morning, the John Postel lecture, and you'll appreciate this. Let me pull this picture up first. I took a picture. It's taken infinite time. At the end of the talk, the speaker was taking questions, and most people were leaving. So the questioners came up to the podium with him. And ordinarily, it looks like a mob. It was a perfect cue. First come, it was beautiful. I so much enjoyed it. See, there's beauty in this. Okay, let's cancel this. What I'm looking for now is this little guy. There. This is an example of an experiment. It's playing blackjack in Las Vegas. And you may or may not know how blackjack is played, but you get a score and the dealer gets a score. And depending upon the relative scores, either you win, lose, or draw. And I've shown you in this picture every square. For example, this particular square here is a possible outcome of the experiment. Namely, in that case, was it this one? He got more than 21. You got 19, so you won, if you know the rules of blackjack. Okay. By the way, what are the odds in blackjack? Are they generally in favor, against, or even? Against, unless you count the cards. And for those of you who want, I'll show you my card counting system. No, I won't, but it works very well. Used to work better. Okay, so every box here is a possible outcome of this experiment. You go there, you play your hand, out comes a result. So all these points here are, in some sense, outcomes. Let me talk about that. There's a set of possible outcomes, and I'll do this in a bunch of outcomes. And then you group the outcomes into classes. What classes have I grouped them into? 3 possible classes. Okay? Basically, what we call results. Namely, win, lose, or draw. many outcomes map into a single result. Okay. And then there's the relative frequency of those outcomes. This is the real world. You go to Las Vegas, you got to think about this. Okay? And basically, it's essentially the relative frequency of the results from the outcome. So example, let's assume we say that the frequency of win is, say, 3/8, and of lose is 3/8, and of draw, say, is 1/4. I just made this up. I made it an even game. It's not even, okay? Okay, now that's the real world. Then along come the mathematicians, and they try to put some mathematics on this. Just a moment. Okay, so the mathematical model, this is the real world. Let me just call it that. Real world experiments. Then there's a mathematical model that tries to talk about that. And we're going to create this mathematical model. And the mathematical model contains a few things. First, it contains something called a sample space. And usually these are mutually exclusive. Outcomes. And I'm using the word outcomes here in particular because I was using the word outcomes up here. So you group the outcomes, individually identify them as a sample space, and typically you use the symbol omega as an element in that sample space. So every box here is an element in the sample space. And you want to make sure that the sample space includes all, the sample space we're going to denote by the letter S, is all possible outcomes. Second thing we do, we have events, which we use to denote by the letter E. And we typically denote them by capital letters A, B, C, etc., where each event is a collection of sample points. Okay? And corresponding to the real world experiments, in our case, they might be win, lose, draw. In fact, you can see what I've done here. The red things are lose, etc. And the third thing we get is essentially a probability measure. And basically, it maps the set of events, item number 2, onto the set of real numbers. And basically, for example, the event A, we use the symbol P of capital A, and that's the real number assigned to the event A. And compared in the real world, P corresponds to what we call the relative frequency. Of the event. For example, what we did in that experiment, we would have said that P of win, the real number associated with the event win, is 3/8. And P of lose is 3/8. And P of draw is 1/4. Now, there are properties of this assignment, okay? First of all, it's got to be non-negative. It's got to be less than 1. So P of any event, it lies between 0 and 1. Secondly, the probability of the entire sample space is equal to 1. And third, item C, if A and B are mutually exclusive, and I'll define that in a moment, then the following is true. Then the probability of event A or event B is the sum of the probabilities. It's equal to P of A plus P of B. And in paren, we'll define mutually exclusive as follows. If A intersect B is equal to A times B, which is equal to the complement of the sample space, which is equal to the null space, namely contains no points, and we denote that by symbol phi, then A and B are mutually exclusive. Oops. And A and B are mutually exclusive. Okay. So this is a very simple setup, and it corresponds directly into the real-world experiment. The outcomes, the results, and the relative frequency become the sample space, the events, and the probability assignment. So that's just justification for this model. It corresponds to the real world in many cases. Now I want to define something else while I'm at it. And by the way, I'm being a little careful in these definitions, going slowly. You've probably all seen this at one point or another, because these definitions creep up on you. We're going to make some very simple, obviously sounding comments, which are going to be very powerful as we go along. So don't say, oh, this is baby stuff, I don't have to think about it. Yes?
It might be a little rusty. Could you remind me what A times B is?
It's notation. We'll write A intersect with B as A dot B. It's just notation. It's not anything more sophisticated. But thank you for asking. Okay. Okay. A set of events and let me define it as some set of AI, where AI are different events, is exhaustive. And that's what I'm trying to define here. Is exhaustive if A1 union A2, oh, by the way, let's assume there are n of these, goes from 1 to n, union dot 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 union A sub n is equal to the entire sample space. I use script S or capital S, meaning the same thing. That's exhaustive. Now, if AI intersected with AJ, and I'm using the shorthand notation now that you asked about, instead of the intersect symbol, if that's equal to the null space, for all I not equal to j, and A1 union A2 union AN is equal to the sample space, namely they complete, then this set, this means that it's mutually exclusive and exhaustive. mutually exclusive, exhaustive. And I usually write that as M-E-E. Now this triplet I just defined, what's the triplet? It's a sample space S, it's a set of events E, and the probability measure P, with the axioms that I mentioned, A, B, and C. Basically form a probability system, as I tried to say earlier. So we're defining that, and here we're defining mutually exclusive exhaustive. Okay, so much so for the setup. Now we're going to define some things. We're going to define something called conditional probability, which you've all seen before. That's what I'm trying to define right now. As the following. The conditional probability of event A, given that event B occurred, is the following. It's the probability notation of event A given that B occurred, the vertical sign means given, is defined as follows. Defined as the probability of the joint event A and B over the probability of the condition, P of B, assuming that P of B is not 0. Otherwise, that's not defined. So what that means is the following. If I got some kind of a sample space, say this blob contains all the possible points, all the possible sample points, and if the event B, say, contains those points, in black,
Testing. Hello? Testing. Can you guys hear this? Okay.
Working now? Is that a yes? No? Okay, great. Okay, let's get back. I want to define something called statistical independence. And by the way, this is the kind of material you should have seen in high school. Statistical independence of two events, A and B, these two events are statistical independence if and only if the probability of their joint occurrence equals the product of the probability of each. And that implies that the probability of A given B is the probability of A. In other words, knowing that B occurred doesn't affect the probability of A occurring. Okay? Next. A theorem. The theorem of total probability. Okay, so here it is. Let the set AI from 1 to n be a set of mutually exclusive exhaustive events. M-E-E. The theorem says the following, that the probability of the event B is equal to summation over all possible events AI, say from 1 to n, of the joint probability of AI and B. I'm having trouble. Okay. Now that looks relatively innocent, but let's manipulate it a little. What it says is, if B is going to occur, it must occur with some other event of all possible other events. And if they are mutually exclusive and exhaustive, then I can add these joint probabilities P of AI and B. Okay. It's obvious. You can prove it, but the proof's obvious. Okay. Now also, let's make some notation, because I'm going to get a different form for this, one that's very powerful. The probability of AI and B we know is equal to the probability of AI given B times the probability of B. From what? From the definition of conditional probability. I'm going to put it AI given B is P of AI and B divided by B, which can be written the other way as well. That's equal to the probability of B given AI times the probability of B itself, probability of AI itself. So, combining what I just wrote down from the original definition of total probability, the probability of B can be written as the sum over all of these mutually exclusive exhaustive events of the probability of B given AI times the probability of AI. I'm going to put a box around that. This relatively simple looking equation, this is an extremely powerful expression. And basically, it says if I want to find the probability of some complicated event B, I don't know how to get it. If I knew what B was given AI, I'm going to give you an example in a moment. It may be that this thing is very easy to write down. It's up to you to invent what the AIs are in the problems you're going to apply. But if you can condition on some event occurring, then it may be very easy to get P of B given AI. And if you can, then if you multiply by the probability of that condition and sum over all conditions, you'll get this more complicated event. So the rule is you have an event whose probability you want. Can't figure it out. Condition it on something, and then that summation unconditions it. And if, to go ahead, if this is still too hard to do, condition it on something else. Multiply the probability of that second condition, and then uncondition it one at a time. Now, I know this just sounds like words to you, you don't quite see the beauty yet, but you will see it when we apply it. It's a very powerful technique. I'm going to show you an example very soon. Okay. So one more thing I want to identify now before we go into some more detail, and that's Bayes' theorem, which you've all heard. And Bayes' theorem says the following. The probability of AI given B we'll stop in just a moment. Probability of AI given B is equal to the following ratio. Probability of B given AI times the probability of AI over the sum over all such terms. I equals 1 to n of probability of B given AJ. Let me make this a J, I'm sorry. Let the subscript here be J. BI given AJ, probability BJ, probability of AJ. Now, can you prove this? I'll show you here how easy it is. That thing on the left is simply, you'll know in the definition of conditional probability, it's probability AI given B over the probability of B. Is the numerator in what I just put in parens the same as the numerator above it? I'm sorry, this is comma, not given. Okay. Numerator is a definition of conditional probability. Denominator is this thing I just circled in red. Proof. Okay. Now let me give you an example. What the idea of Bayes' theorem is that it reverses your focus. Instead of figuring probability of A given B, you can work happily only with B given A. Instead of A given B, it's B given A. And that may be easy. I'm going to give you an example right now. Okay? You go to Las Vegas. There are two dealers you may encounter. They're twins, and you can't tell them apart. Okay? Dealer H is honest. And if you play with him, the probability that you lose, given you play with the the honest dealer, is a half. He's fair. There's another dealer, he's the cheating dealer, D sub C. The probability you lose, given you play with the cheating dealer, is say number P. Okay? Okay. You go to Las Vegas. Two equal dealers, you play with one of them. You lose. You say, son of a gun. Can I prove, knowing this information, that the fact that I lost strongly suggests he was a cheat, so I want my money back? You know, what can I say? You say no. Okay? Or, okay. So let's do it. So you play, you lose, and you want to calculate the probability that the dealer was a cheat given that you lost. And if that's high enough, you go to the lawyer and you try to get your money back. Okay? So let's calculate this thing. Okay? Using Bayes' theorem. That's the probability that you lose given the dealer was a cheat times the probability the dealer was a cheat. Over all possible cases, with only two, probability you lose given the dealer was a cheat times the probability the dealer was a cheat, plus the probability you lose given the dealer was honest times the probability the dealer was honest. Now, it's not at all obvious how to calculate this thing. But you look at these guys, every one of these you know. So let me write it out for you. That's equal to, with probability P, you will lose if you play with the cheating dealer, and the probability that he was a cheat was a half over the same thing, P times a half, plus what's the probability you lose if you play with the honest dealer? A half. Probably you ended up with an honest dealer? A half. And you're done. And this turns out to be trivially 2P over 1 plus 2P. So, it was easy to do, wasn't it? You had all the information in the setup, but it wasn't obvious how to do this, how to find this baby that you're looking for, namely this thing. And it became trivial with Bayes' theorem. Now, if little p was 1, which means if you play with the cheating dealer, you're surely going to lose. Even then, the fact that you lost only has a probability 2/3 that he was a cheat. So you're not going to win the case. The judge will say, not enough is heard. If this number was close to 1, it would. But it can't get there. So too bad. But as an example, it's a handy example. Okay, let's take our break and come back in, say, 6 minutes, because I gave you a little break before. Okay. Do I have the course code? I'll find out. I may need some help finding that. Let's see. So what do you want the course?
There's like a code for the Gradescope that lets you access it.
John, can you give me a hand here? He'll help me with you. Okay. Yeah. Well, if you depending Appendix 2-1 doesn't do it for you, then sure. Okay, okay, sure, okay. He wants the code to get onto Gradescope. On Bruin Learn, we want to do it. Is there a code for this thing?
We need to, you enrolled with PT, right? Yeah. I think we need to manually add them to Gradescope.
Oh, okay, so let's go to the PT thing. Where do I find that one? What do I want?
I think we need to go to Gradescope.
Just Gradescope, not the Bruin Learn Gradescope or the Bruin Learn Gradescope? Let's see.
I don't know this one.
Oh, well, it was, is Chloe here? Chloe,
Chloe?
I need you. You're dismissed. Let's see. Chloe, I need to give some of these guys PTEs. They were looking for a code. Where do I go? I'm in the wrong place. I want to go to Bruin Learn, do I? My UCLA? Okay.
Okay, so we can access this in Bruin. I can get
Well, I have to give you the PTEs though, right?
Wait, no, we already got this.
Oh, you do?
Oh, we're good. Okay, we got it. Sorry.
Oh, okay. Oh, good. It wasn't doing that before. Okay. Now, what do I want? This thing here?
Yeah.
It doesn't, it's not hard. Students, is it? Grades? No. Here's grade scope. Shall I go there? No. Which one? People. Oh, people. Okay. It should turn on. Oh, there it is. Here, people? Oh, add people. I see. It's not giving me, not giving me PTEs here. Who told me this last time? Was it you?
Not me, I think.
Thought it was John, actually.
Yeah, I thought.
John? John? We need you again. You're reelected. I'm back on this site, but I don't see where to get the PTEs. Do you remember how to do that? Or get one of these? Up here, maybe?
My UCLA.
On my...
They're here. Doing our time.
This one?
Here.
Oh, Jesus.
Oh.
That's a quiz problem, huh? 9, okay, here. Here we go, okay. Student ID. Who wants a who needs a PTE? What's your student ID? 3056 25 430. Let's see if that works. I'm going to sign it. 48795. And that's you? Wrong, John?
Yeah, I think the CD is 48795. Yeah, I think so. You could use
There
that.
David Zhang.
Yeah,
Okay.
you could use that. 48795.
You sent me an email, didn't you, earlier? Okay. Anybody else need a PTE? No? You have a question? Yeah.
For the makeup electricity recorder, because I have a specific question that I have to do in the exact.
Not clear. I may give you access to what's on the screen. I'll tell you what the trouble is. If we make all the recordings available, nobody's going to attend the class. That's what I'm worried about. So, yeah. I understand. I don't want to disadvantage you. Where's your sheet? Check with me after class, okay? I think we can do it. I don't want to disadvantage you to make sure. Okay. All the class, just one of them, or all 3 Fridays?
Every Friday at 1 to 4.
I mean, I
Weekend though.
yeah, I could do another hour, but I think it's more likely to hit people if I did other than 2 to 4. Okay, check with me after class. Okay. You, I can't hear you.
Was it ever mentioned if the notes you're writing on the screen will be posted or?
Wasn't planning to.
Okay.
Wasn't planning to.
Okay.
Because I'm not quite, but almost going verbatim from the book.
Okay.
So the book is more detailed than what I'm saying, and the penmanship is better.
Yeah, okay. No worries.
Okay. Okay. Sure.
When is the midterm going to start? You know,
I haven't.
Week 6, I'm just wondering whether it's the Monday or the Wednesday of week 6.
Okay, I'll tell you. I think I
I'm
have
just
it.
trying to figure out if I have to take 3 midterms back to back or not.
See, the problem is now that the holidays jumped in, but it shifted the number of lectures. Well, let me check it. Now, just 1 second.
Yeah.
Yeah.
Because the only reason I was asking is that the way my schedule is disorder, I have classes from 12 to 6 on Monday morning. Like 3 lectures back to back.
So you're going to get.
Yeah,
okay,
so
let
I'm
me
just hoping that all 3 midterms are not on the same day.
let me just see. Let's see. Just a
Because
moment.
the finals are a different day. So that's fine.
Okay.
It's just the midterm.
It's an early one. Let's see. So I have. Just a moment. Here's somewhere. Okay. I scheduled it for lecture 11.
When is that in the past?
So let's. So
Lecture 3 will be in the next week.
yeah. So
4, 5 is week 3.
We'll figure it out.
6, 7 is week 4. 8, 9 is week 5. 10, 11 is
Seven.
week 6. So Wednesday is week 6.
yes.
Right?
Is that what? That's what I've scheduled now. So let me put the date down as well.
I think that's
Is that going to work for you or not?
That's fine. I think that's fine. Yeah.
Well, no, I don't want to give you a problem though. So let's see. Let me go.
No, I
to
think
one.
that's Southampton, right?
Let's find out. So this is week. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the 12th.
Well, no, next Monday is holiday, right? That's why.
But it's making up a Friday. But you're right. And I think does the Friday come before the midterm? In which case it doesn't matter.
Wait, what about what Friday? There is no discussion for the class, right?
Yeah, were you here at the beginning of the class today?
I came in like a minute or so late.
So you missed. Let
What
me show you.
happened?
What happened? That's what happened. These 2 dates, no class. But you notice that this one is made up in January. So as far as you're concerned, the same number of classes will have taken place. And this one is made up made up on this day before that. So what day did we say the exam was? It was the 11th lecture, right? And it was around Feb.
Oh, that means those days you're going to be lecturing instead, like on Fridays?
Oh, no, it could be an exam. But it shouldn't be.
Wait, so what's March 6th?
That was a schedule change, because I have to be out of town then. March 6th is made up on Feb 16th. You know what? Let me work out the numbers that we're trying, the arithmetic.
Oh, wait, actually, could you just email, like, put an announcement about this and the midterm date, like, whenever you figure it out?
Okay.
No,
And
no.
and the finals okay.
Final's fine, yeah. It's just like the midterm day and then I didn't know about this, so it'd be nice to.
Do me a favor, send me an email, remind me to do that, I'll do it tonight.
I'll do it.
What's your name? Sahil.
Yeah, that's
Okay, great, okay, I'll wait. I can't see it. I heard it.
I'll be adjusting it, but it should work.
Rohit? Okay, you got away with it. You had a longer break than you should. My fault. So let's see now. We want to go to. So we just finished our little cheating dealer situation. Okay, let's continue now. I want to introduce something you should know something about, something called random variables. Now, we already have that triplet, namely the probability system. We have the sample space, the set of events, and the probability measure. Now, a random variable is a variable whose value depends upon the outcome of a random experiment. Namely, some sample point is chosen, and I want to assign a number to that sample point. I want to assign a number I'm going to write as x as a function of the sample point. And it comes from the real numbers. And it's basically the value that the random variable takes on. It's the value that the random variable takes on when omega occurs. So in some sense, this thing called x of w, x of omega, essentially it's a mapping onto the sample space. So our blackjack example was the following. Let's assume for the moment there's only 3 outcomes in the blackjack example: win, lose, or draw. Those are events. I'm going to claim those are the only outcomes of the experiment. Then we said that P of L equals 3/8. P of win equals 3/8. And P of draw equals 1/4. When you lose, this random variable is how much you lose. And the answer is going to be, in this case, say you lose minus $5. And when you win plus $5. And when you draw, you win 0. Which means that this random variable, x of these 3 possibilities, is the following. It's equal to plus 5 when basically w occurs. It's 0 when draw occurs, and it's minus 5 when lose occurs. And in some sense, I can draw that sample space looks like this. Again, if there's only these 3 possibilities. This is win. The random variable there is plus 5. Well, let me do it differently. Let me write down simply the probability in there, make it easier. The probability here is 3/8. Draw is 1/4, and lose is 3/8. And there is essentially a mapping onto the real line. And if this is 0, then the event win maps onto the value plus 5. The event lose maps onto the value minus 5. And the event draw maps onto the value 0. That's the mapping. So the domain here if you will, of the random variable are the events. And in this simple example, it was win, lose, draw. Ordinarily, it's individual sample points. That's what domain is. The value of this random variable x or its range. So I'm defining what I mean by range. And what we want the probability that a random variable takes on some values. That's typically what we're after. Probability that the random variable takes on some values. For example, what's the probability there are less than 10 people in the queue? I want to find that. That's going to be an interesting question for our queuing system. Okay? The events that we're talking about, say x, the random variable, equals some value, little x, that's a number, is defined as, that notation is defined as those sample points, omega, such that x of omega equals this number, little x. That's what I mean by the bracket x equals little x. And the probability of an event is the probability that the random variable x equals little x. What is that? That's a notation. It's the probability that x of omega equals little x. I'm just showing you some notation for brackets and p's. For example, the probability that x equals plus 5 in our little example equals 3/8. We know that, etc. Probably minus 5 is 3/8, etc. And that was the mapping I just showed you above. Very simple set of definitions of what a random variable. What is it? It's a number assigned to the possible sample points or events in the sample space. Okay. Now we're going to define some functions of these probabilities. I want to define something called the probability distribution function. And in parenthesis, I'm going to give you the shorthand notation for that. It's a capital P, capital D, capital F. And the fact that they're capitals is important, as you'll see in a moment. It's also known as the cumulative distribution function in probability theory. Cumulative distribution function. Which is often written as capital C, capital D, capital F. We won't use that. We'll use capital PDF. Now, what this thing is in meaning, it's the probability that x, the random variable, is less than to some number, little x. What is that? It's a set of points such that x of the sample point is less than or equal to little x. That all the x's associated with those are less than or equal to number x. And we have special notation for that. Capital D, capital D, D, capital F is written as capital F for the word function, sub x, what the random variable is, of the number x. It's defined as the probability that x, the random variable, is less than or equal to little x, a number. What are its properties? Sorry, my writing is terrible. First of all, f sub x of x is always greater than or equal to 0. Secondly, f sub x of infinity for proper functions is always equal to 1. And f sub capital X of minus infinity is equal to 0. Namely, the darn thing looks like this. It's a non-decreasing function, which in the limit of large x is 1, and the limit of large negative x goes to 0. This is x, and I've just plotted f sub x of x. And trivially now, the difference between this distribution function at a value b minus its value at a is simply equal to the probability that a less than x less than b for a itself less than b. And it's also true, therefore, that f sub x of b is greater than or equal to f sub x of a, again, for a less than or equal to b. Now, this, what I've drawn in red here, is for a continuous random variable. There are discrete random variables, for example, the blackjack game, which looks like this. Let's draw that distribution function for a blackjack game. There are 3 critical points. If I want to plot f sub x of little x. X is the random variable, which is the minus 5, 0, and plus 5. So let's identify those 3 points. For little x less than minus 5, what's the probability the random variable could take on a value less than minus 5? 0, it can't. So it's 0 here, and at the point minus 5, it jumps up with the probability 3/8. Then it moves with the same constant to 0. Until at 0, it jumps up by a quarter, namely it jumps up to 5/8. And then it goes out to plus 5, and it jumps up to 1. So clearly, this jump is 3/8, this jump is a quarter, and this jump is 3/8. This is an example of discrete random variable. The thing above is the example of a continuous random variable. All of them obey the properties I've shown here, namely these 3 properties here. Now, there's something else besides a probability distribution function, as I defined here. There's something else called a probability density function. Second definition. So I want a probability density function. And I write that in shorthand as little p, little d, little f. So if I say it, you can't tell the difference. You have to see me written, have me say it's lowercase, uppercase, or distribution, or density. Okay? Lowercase is important. And what is it? It's a differential of the capital. So f sub x of x, the probability density function, is defined to be the first derivative of the capital one, of capital F sub x of little x, of the capital PDF. And inversely, the capital is equal to the integral of the little f. It's the integral from minus infinity to little x of f sub x of y dy. F sub x of y dy. And the main property is that that quantity is never negative. It's always greater than or equal to 0. If you look back at this comment here, that f sub x basically is monotonically increasing, its slope is never negative, and little f is the slope of the capital F. And it's also true that the integral from minus infinity to infinity of little f how much is that? That's right, it's 1. It's all the probability. And similarly, the probability that x lies between a and b is just the integral of the density from a to b. Little f sub x of x dx. Again, this again for a less than b. Okay. Now you've seen all of this before, I hope. If not, it's just notation. The distribution, the probability distribution function, capital P df, is a little easier to understand, but little f is a little easier to manipulate. So we're going to use both. We'll use little f quite a bit. Okay, let's take an example. I'll put this in blue now. The example I want is the exponential function. This is the most popular one we're going to use. In queuing theory, it occurs all the time. And it's the following. It's the case where the distribution function, capital F sub x, is equal to one of two things. Either 1 minus e to the minus lambda x, where lambda is just a number, for x greater than or equal to 0, or 0 for x less than 0. And it looks like this. That's, well, I'm sorry, that's a little one, I'm sorry. Let me erase that. It looks like this. And this value, of course, goes to 1. It starts off at 0, this little x, this is a capital F sub x of x. And the expression is what I gave in blue. Similarly, its density, let me write this in blue. Little f sub x of x is equal to what? We'll just differentiate the thing above, and I'm going to get lambda e to the minus lambda x for x greater than or equal to 0, and 0 for x less than 0. And it's going to look like the following. Going to look like this. That's an exponential where the value at the origin is lambda, and the expression is lambda e to the minus lambda x. It's a very important, very common function. And notice it happens to be the Laplace transform we studied as a good example. And it's going to appear in our equations. That's one of the reasons we like the exponential. What's the other reason we like the exponential? Because nature gave it to us. It's the basis of the transforms. It turns out to be one of the reasons the exponential is so useful mathematically But by the way, it also happens to be useful in practice because the exponential function, again, appears in many of our queuing systems for good reason. It has to do with related to the limit of some kind of renewal process, which we'll talk about. Okay. So we have that this simple function here. Now, what I've shown you is in this case here, we've shown you a continuous system. What's wrong with my pen? The one above, we showed you a discrete function for the blackjack. And they also are mixed random variables. An example of a mixed random variable would be the following. Let it be the life of an automobile. When you buy an automobile, it could be that it's dead on arrival. As soon as you buy it, it doesn't work. It's a really bad lemon. And let's say the probability of that is some number p. And it's an exponential lifetime if it's not dead on arrival. Not dead on arrival. And the PDF in that case is what I just described. It'll be lambda e to the minus lambda x, where x is the lifetime. I'll use t actually for time. Why not? That's a t, believe it or not. My pen is giving me some trouble here. Okay, what does that look like? Let's draw its PDF. Rohit, do you have that pen that's live? I think I'm running out of power. Oh, you're not using it? Okay, thanks. Let's hope this baby works. You recognized it, I think. Nope. You sure it's charged? Help. This is the new one. Here it is.
Could I go to your settings?
Yeah, sure. Here, there, yeah. Here's the Apple Pen. Let's see. Let's touch this. It's got 100% load, so that should be it, right?
This one.
That's the good one. Good. Okay. Good. Okay. Back in business with the pen that works. You should always have lead in your pencil, whatever that means. Okay. So let's plot some of this. Let's plot, for this particular case, the distribution function, f sub x of x. What's the value when x equals 0? It's an amount p with probability, the lifetime is 0. X is the lifetime. Probability p is 0. And after that, it's exponential, which goes to 1. And if you look at the density, if you look at the continuous part, it looks like that exponential, which happens to be 1 minus p, the probability that it's not dead on arrival. times a lambda e to the minus lambda t. I'm plotting it versus x, so I'll use x here. This is f sub x of x. The question is, what goes on at the origin? Little f is the differential of capital F. And I'm differentiating a step function. Now, some of you have seen that before and some of you have not, okay? So let me pause before I answer that question here and spend a moment talking about this. I want to define that funny step. I want to define something called delta of t, and it's in the tables, in your transform tables. And it's called the unit step function. And what is that? It's a function that looks like this. Versus t. I'm going to plot delta of t. It is 0 up until 0, then it jumps up to 1. That's why it's called unit step. Oops. From there on. Very simple function. It's a very useful function, it turns out. And it turns out that delta of t has a transform 1 over s. Sorry, I'm jumping around here a bit. Now, I'm not looking for that, because up here on the capital F function, I've got a step. But I want its differential over here. So let's talk about the differential of delta of t. Let's define the differential of delta t with respect to t. By definition, we're going to use notation. It's u sub 0 of t. And that's called the unit impulse function. Engineers love it. Mathematics hate it. Mathematicians hate it. Yes? Depends which mathematics course you took. Okay? Now, u sub minus 1 would be delta of t. You're right. Some mathematicians use this symbol for what they call the impulse function. Okay? We're calling it basically the step function. It's notation. It's what engineers typically use as notation. Okay. Just a definition. You can't argue with the definition, by the way. Okay? And basically, it's something that occurs at 0. So let's look at it. Let's try to create this u0 of t by playing an interesting limiting game. I want to consider a function which looks like this. It's a rectangular pulse over the interval from 1 over 2a, let me just get this. Let's use alpha, minus 1 over 2 alpha. Sorry. Minus 1 over 2 alpha to plus 1 over 2 alpha at a height basically alpha. So first of all, what is the area of that thing I just drew? 1. No matter what alpha is, okay? Now suppose I double alpha. If I double alpha, I'll get something that looks like this. And if I double it again and keep doing that, I'm going to be starting to get something like this. And in the limit, I'm going to get something whose area is 1, which is very narrow, and whose height is infinity. And I'm going to denote that with this symbol. It's just a vertical arrow. Oops. It looks like this, with value 1. That's a unit impulse. We'll call that u0 of t, 1 for the unit. Its height, its value is infinite. The arrow indicates it's going to infinity. Now it turns out that u0 of t has a Laplace transform. And what is that? It's the integral from minus infinity to infinity of the function u0 of t e to the minus st dt. And pray tell, what is that? It only has value when t is 0, right? This is t here. So when t is 0, e to the minus st is 1. So I'm integrating this u0 of t, and what is its area? It's 1. So this whole answer is 1. I told you earlier that the transform of the integral of that is 1 over s. The integral of the differential of this is 1. The transform of that is 1. Okay. Now, having said that, I'm going to go back to my little example of the dead on arrival car. Then what can I draw where the question mark is? I'm differentiating a function which is 0, takes on the value p, and stays on the value p forever. What is that? It's an impulse of what area? P. So what I'm trying to do is introduce you to something we're going to see later, the case of mixed, discrete, and continuous. There's the discrete component, the jump at the origin, and the continuous portion over the rest of it. Okay. So much so for introducing the distribution function and the density function for random variables. Okay, now let's go on to a new concept, the concept of expectation. So the expectation of a random variable, say x of omega, is the following. It's written as capital E of the random variable, in this case it's x, which we write as the random variable x with a bar over it, meaning average or expectation. And it's defined simply as the integral from minus infinity to infinity of little x, f of x dx. And that's known, as you recognize, as the mean of the random variable x, or the average value of x, or, as I'm saying, the expectation of the random variable x. Okay. Now let's look at something called a function of a random variable. Say we have a random variable y, which happens to be some function of another random variable x. For example, g of x could be x squared, or it could be some polynomial x, or it could be the square root of x, some function of x, okay? So what is the expected value of this new random variable, y? Well, by definition, from the equation above, it would be the integral from minus infinity to infinity of some variable y times the density of y dy. And by the way, what I should have put up in the upper equation, I should have put a capital X over here to remind you it's for the random variable x. Now this is not easy. Let me say this is hard. Why is this hard? If I tell you the random variable x and I give you its density, and I now want the expectation of y, what's difficult about that computation? What don't I know? Yes? I don't know the density of y. You give me the density of x when you give me x. Okay? So I certainly know, let's get this. I know this. That's given to me when you give me the random variable. But I don't know this, as was said. Now comes a really important thing. It's called the fundamental theorem of expectation. And it's the following. It says the expected value for the random variable y, I'll write it that way for the moment, is equal to the expected value with respect to x of g of x. Now what is that? If you write it in terms of its density, notice the expectation I'm taking with respect to x here, which I was taking with respect to y here. So when I do that, I'm going to take the integral from minus infinity to infinity of the function g of x times the density associated with the capital X, which is f sub x of x. So if this is true, and it is, then I don't have to find this guy. Sorry. I don't have to find this guy. I just need this, which I know. And the g, which I know, because you defined y as a function that you give me, little g. So I'm in good shape now. Now this turns out again to be something we're going to use over and over again. But remember that to find the expectation of a function of a random variable is that function times the density of the original. That's the same as this, but written in a much more usable way. Okay. Now let's go on and look at the sum of two random variables. Sum of x and y. I want the sum x plus y. Let's ask, what is the expectation of that sum? It turns out that's the expectation of x plus the expectation of y, whether or not they're independent. Now, can anybody suggest how you might prove that? I'm not going to do it. It's in the book. Yes? Excuse me? Be more explicit when you say linear. In order to form the expectation of x plus y, you're going to use a joint density, f sub xy of xy, which turns out to be the product of f sub x of x times f sub y of y, because they're independent. Excuse me, it's always the case, because you integrate on one of them. It'll drop out. Try to prove this just for yourself. It's not a homework assignment, it's a suggestion. It's very easy to do. Which means that the expectation of a large sum, x1 plus x2 plus xn is equal to the sum of the expectations. And the important point is that's true whether or not they're independent. Let me show it to you since nobody lit up a light when I asked the question, okay? Let's try the case for 2, x and y. Expectation of x plus y is equal to a double integral, as you suggested, of the sum x plus y, little x plus little y, of the joint density f sub x y of little x little y dx dy. That's the way you would form it. Now, because of the summation in the leading term there, I can write this as the double integral of x times all of that, of the joint density x, y, x comma y, dx dy, plus the obvious term, plus the joint density of little y, f x y of x, y, dx dy. Now notice, when I want to integrate on y in this first term, let me point to it carefully. When I want to do this integral on dy, this x is independent of y, it can come out. And I'm integrating f of xy on y. So I'm integrating the whole this density on y, so I get 1. So if I get what out of that, I'll get this is equal to the integral of what I pulled out. This is on y and on x, on basically x. And what's left when I do that, I've got the simple density of x itself. And similarly, the second term becomes the integral on y of y, f sub y of y, dy. And clearly, that's equal to the expected value of x plus the expected value of y. So that's the proof I asked you to try to do for homework. I just did it for you. Okay. So another way to write that is you have a random variable x plus y, and you want the average of that. That's equal to the sum of the averages of each. That's another way to write it. That's important, whether or not they're independent. I did not need independence to go from here to here. Okay. Now, let's look at products instead of sums. I want the product of xy. Now, if they're independent, it's going to ring in a minute. If they're independent, then you can show that the expectation of the product is the product of the expectations, but not otherwise. And similarly, the product of functions of independent variables also has the same property, namely the expectation of g of x times, say, h of y is equal to the expectation of g of x times the expectation of h of y. But this is if they're independent. We're going to stop here because we have a little bit to develop to get to the moments. So let's stop right here. Our next class is Monday. You've got your homework assignment. Everybody able to find the homework assignment in Do and Learn? I'd have trouble finding it, I think, but it's in there. And it's due next Wednesday, a week from today. And the solutions will be available on Friday next week. you should be able to do most of that. You may not be able to do the 8th problem yet. You'll need a piece of Monday to finish that. Or if you're very good, you can try it. Okay, but it's not due till Wednesday. Yes? Oh, this is the holiday? Oh, Jesus. Okay. Homework is still due on Wednesday because, oh, no, it's not. Okay, hold up on the 8th problem. Okay? And we'll make that the first part of the next assignment. So you're not going to get away with it. Okay. So we're meeting next Wednesday, and when was the makeup class? I forget now. Thank you. Oh, the makeup. Okay. So we're going to meet next Wednesday and then the following Monday. Okay. And the makeup is here. Okay, so let's talk about those who are concerned about not being able to make those makeup classes.